All right, this is the 5.2 video for Calculus AB, 5.2 intro video. We're going to be looking at the natural log function again, kind of like we did in section 5.1, except we are going to be looking at integrals that end up involving the natural log function. So remembering what we talked about in 5.1, I hope that we can maybe think about what the answer to this first little thought is. This first example, the integral from the integral of 1 over x dx. Well, if you remember that the derivative of natural log is 1 over x, then perhaps we can remember that, or we can reason to the idea that the integral of 1 over x would have to be natural log of x. Now for now, we're going to go ahead and put an absolute value around that x. We'll get into that a little bit later in more detail. So for now, don't worry about it too much, but technically it needs to be there. Okay, and then of course we could also have a composite function, and this is going to be by far the more common situation. And so we'd be looking for this pattern right here. And this is, I don't want to skip over this too fast here. We're going to be looking for a fraction. This is going to be really the first. This section is going to be the first time where we look at an integrand that is a fraction, and we're going to be okay with it, and we're going to try to work with it. In the past, we've tried to take any fractional integrands and turn them into something that's not a fraction. So keep that in mind here. So if we see the integrand being the pattern of u prime over u, in other words, the numerator is the derivative of the denominator. Exactly, not close or almost, but if the numerator is exactly the derivative of the denominator, then what would follow is this. Natural log of u, the absolute values in there, plus c. So that pattern is quite important, where you've got a fractional integrand, the numerator is the derivative of the denominator. If that's the case, then we will end up with natural log of u plus c. One little note about this that I've seen in the past, so I thought I'd mention it to you. If you see integral of 1 over x dx, I'm sure you can imagine it would be tempting to write this. Integral of x to the negative 1 dx, and then try to use the power rule. And so let's do that really quick and see what happens. If I do that with the power rule, we would add 1 to the exponent, and then we would divide by the new exponent. And so that would give us x to the 0 over 0. And of course we have an issue there. We can't divide by 0, and so we'd have to, maybe we'd look at that and say, oh wow, maybe the antiderivative doesn't exist. If you're ever in a situation like that, it probably means that you should have considered natural log. And so just keep that in mind. I've seen that happen to plenty of folks, and I thought I'd just throw that out there for you ahead of time. Okay, let's go ahead and do a few examples here. Number 1 says the integral of 2 over x dx. First thing I think I would recognize here is that the 2 is a constant multiple, and so I can bring that out, and so I'd get 2 times the integral of 1 over x dx. And that would lead us right to the form we just talked about. The integral of 1 over x dx is natural log of x. So I would write as a final answer 2 times the natural log of x plus c, and that's it. So the key is to recognize that form. The key to recognizing is to seeing it a lot. So please do practice with these and get used to that form, and I think you'll find good success. All right, let's go ahead and move on to number 2. Okay, so you can see comparing number 2 to number 1 is a little bit more complicated. We look at obviously the integrand, we see it's a fraction, and so I would encourage you, when you see fractions now as integrands, please consider natural log. Please consider natural log as a possibility. So what we would do here is we'd say, all right, great, it's a fractional integrand. The next question we want to consider is the derivative of the bottom the top? Is the derivative of the bottom the top? So obviously the denominator is 4x minus 1. We think about the derivative of that. The derivative of 4x minus 1 is 4. And so the answer to that original question, is the derivative of the bottom the top? The answer is yes. And so because of that, we can directly find the antiderivative. The antiderivative would be the natural log of 4x minus 1 plus c. And this might be a place where we look at this and say, wow, where did this 4 up here, where did that 4 go? Really, this is just going back to the inside. It came there as a result of a chain rule. And so it goes back in when we undo the chain rule. If you wanted to check this answer, you might be able to see where the 4 comes from. It might help you to see where it actually goes. So if I did the derivative of natural log of 4x minus 1, based on what we did in chapter or 5.1, we would see something like this: 1 over absolute value of 4x minus 1 times, wouldn't we have to multiply by the derivative of the inside? So it would be times 4, and you can maybe then see where the 4 comes from. And so if we were to reverse that chain rule, if we were to reverse that derivative, the 4 would just go back inside. And essentially, you look at it and say, well, it kind of disappeared. Well, it kind of did. It just went back inside because that's where it came from. It came from the inside, so to reverse it, it's got to go back to the inside. Okay, let's go ahead and look at our final example here, number 3. And number 3, once again, we've got a fraction, and obviously, number 3, the integrand is more complicated yet, right? It's got a whole lot more going on. And so we want to, consider, okay, this is a fraction. In the past, we've tried to make any integrand that's not a fraction. We've tried to turn it into something that's not a fraction. But let's go ahead and stay here for a second and see if this does work out based on natural log. So we've got the denominator there, obviously. I'm going to go ahead and write that down. The denominator is u equals 5x cubed plus 15x. And for this to work out for natural log, the numerator has to be the derivative of the denominator. So I'm going to go ahead and write u prime. We're going to figure this out. So u prime equals 15x squared plus 15. So now we compare that to the numerator, and we can see that the numerator is not equal to u prime, right? And so we might, be tempted to think, well, this is not natural log. But if you remember from back in 4.5, we are allowed to make adjustments as long as we just multiply by a constant. So maybe ask yourself one more question. Is it possible to multiply the top by a constant to make it work, this pattern work out? And it is, right? If we were to multiply the numerator by 15, then this would actually exactly be this natural log pattern where the derivative of the denominator is the numerator. But of course, we can't just multiply the top by 15 without making an adjustment. So what I'm going to do is multiply the outside by 1/15. This is Timmy messing up the chain rule like we talked about a little bit in 4.5. We could also use u substitution. I kind of started setting that up there and realized that I could just multiply by a factor of 15 to make this work. Okay, so here's what happens. I'm now ready to find the antiderivative, and I can do this directly because the derivative of the denominator is the numerator. Whenever you have that pattern and you're integrating, you can go directly to natural log. So this would end up being 1/15 natural log of 5x cubed plus 15x, and then we don't want to forget the plus c, and we've got it. We got it at that point. Again, if there's any doubt in your mind that this is correct, I would encourage you to take that answer right there and differentiate it. You should end up with what we had for an original integrand. I think you'll see that that's the case. Okay, so that's it. Hope that went well for you. We will practice more in class when I see you next time.